When we're thinking about continuity, we're not always going to have the graphs of functions. Sometimes we'll only have their equations. So we need to talk about continuity properties of different types of functions so that if we don't have their graphs, we can still think about continuity. We're going to focus on the first two here. The first one says polynomial functions are continuous everywhere. Remember that polynomial functions, these are functions that have positive whole number exponents, and there's no variables in your denominator. So these are generally nice functions to work with, and when we say they're continuous everywhere, we don't really have to show any work for that. We can just say, well, it's continuous from negative infinity to positive infinity, which would be everywhere. So these are really, really nice functions to work with because they're really not going to give us a whole lot of problems. The second part here says rational functions are continuous everywhere except for x values that make the denominator equal to 0. When we talk about rational functions, these are your functions that are going to look a little bit more like fractions. We're going to have some function of x divided by some other function of x. So if you see something that looks like a fraction, or if you have a variable in your denominator, then chances are that's going to be a rational function. We'll talk more in the next video about root functions, but those are a little bit more complicated. We'll talk about those in the next video. So first, I just want to determine where each of these functions are continuous. So I have two functions here. The first is r of x equals x squared divided by x plus 1 times x minus 4. So here, first we need to determine what type of function are we working with. Here we have a function of x divided by another function of x. We've got something that looks like a fraction, so this is going to be a rational function. Now we said if we're working with rational functions, they're continuous everywhere except for x values that make the denominator equal to 0. And hopefully that makes sense, right? We're not allowed to divide by 0, so we're worried about having 0 in the denominator. So really all we need to do in situations like this is take that denominator and set it equal to 0. So I'm going to take x plus 1 times x minus 4, set it equal to 0, and we'll solve for x. This is nice because it's already factored. You may need to factor this side before we can do anything else, but since it's already factored, we can take each factor and set it equal to 0. So we'll have x plus 1 equals 0, and x minus 4 equals 0. And then if we solve each of these equations, we're going to end up with x equals negative 1, and we'll end up with x equals 4. So it's continuous everywhere except for these two x values, except for negative 1 and 4. So now we need to talk about where this function is continuous. And again, I want to give my answer using an interval notation. If you are new to interval notation, or even if you're not, even if you just want to take your time with these, I would encourage you to just draw a little number line here. And we're going to plot those two numbers on here. We've got negative 1 and we've got positive 4. Those are the two numbers we're worried about. So we're saying it's continuous everywhere except for these two values. So essentially I'm going to have three different intervals. I've kind of taken my number line and I've broken it up into three different spots. I've got this part right here to the left of negative 1. Let's just start with that. I'm going to write an interval for that part that I've highlighted there to the left of negative 1. My left endpoint, since this goes to the left forever, would be negative infinity. My right endpoint would be negative 1. And we're saying it is not continuous at that x value. It's not continuous at negative 1, so we need to use parentheses around negative 1 to show that that number is not included in our set. So we've got negative infinity to negative 1. Then we've got this section right here between negative 1 and 4. So this one hopefully is a little bit easier to see. My left endpoint would be negative 1. My right endpoint would be 4. Again, both of these two numbers, our function is not continuous at them. So I want to use parentheses around those to show, hey, it is not continuous at those two x values. So those numbers are not included in our set. Finally, we've got this area to the right of positive 4. So if I wanted to write an interval for that side, we would say positive 4 to positive infinity. Again, parentheses around both, around 4, because that number we don't want to include in the set. It's not continuous there, and we always use parentheses around positive and negative infinity. And then I'm just going to put a union to connect each of these. Again, you can use a union or you can use a comma. I don't have a strong preference either way, which notation that you use. I believe our book does use the union notation though. And that's it. It's continuous on these intervals. So as long as we're not taking -1 and as long as we're not taking 4, we're not going to have any problems. This function is continuous. So it's continuous on negative infinity to -1, -1 to 4, and 4 to positive infinity. Next up, part B, we've got f of x equals x to the 4th plus 2x plus 1. Here, this doesn't really look like a fraction. We don't have any variables in the denominator, so this is not a rational function. And if I scroll back up to look at my rules here, this is, in fact, going to be a polynomial function. Polynomial functions are continuous everywhere. So sure, we could say continuous everywhere, but we want to use interval notation. And if you wanted to use that technique we just used of drawing a number line, it's continuous on this whole number line everywhere. I would end up highlighting the whole dang thing. So I would say, okay, well, it's continuous, my left endpoint, it goes to the left forever, so it's continuous from negative infinity. There's no breaks or anything like that. There's no points I need to worry about. Going all the way to the right then, it's continuous from negative infinity to positive infinity. So if you have a polynomial, there's really not any work to be shown. You can just say, hey, this function is a polynomial, so it's continuous on negative infinity to positive infinity. There's really not anything else we need to do for this particular problem.